So eta w is a question mark, uw is a question mark, we don't know what it is. So we are going to introduce what is called an inner velocity scale, because the moment I know uw, eta w is straightforward. So let's introduce what is called an inner velocity scale. This uw in literature we usually call this uw is usually represented in literature as u tau or u star. Some of you asked many lectures before, the URMS divided by u tau, what is that u tau? So this particular u tau or u star has a name which is called, we call it wall friction velocity. Okay, and u tau by definition, this u tau, or you can say u star square, is nothing but your tau w by rho, which is of course equal to the sum of your turbulent shear stress and the viscous shear stress here. So u star square is nothing but u star square by definition is tau w by rho. So tau w by rho is easy. If you measure turbulent shear stress, then u star is revealed. So then you have a velocity scale that you can use to non-dimensionalize your mean flow or other statistical quantities, RMS, mean velocity and so on, to get what is called an inner scaling. Okay, so inner velocity scale is revealed, and that means now I have inner length scale also is straightforward to see. An inner length scale. Okay, so this inner length scale is eta w, right? So this eta w, I already said this is nothing but your nu by the u star here, u tau or u star. And when you have this, u star is known, I can compute the inner length scale, and this inner length scale has a name which is called viscous length scale, simply because it depends on the viscosity. So I have, this is called a viscous length scale. Okay, this is your nu by u star. Okay, and we also do what is called inner scaling. So I'll write down here what is called inner scaling, that we already saw in the graph URMS divided by u tau, right? So many times the data is represented in a non-dimensional fashion, all your velocities and RMS. So when we do this inner scaling, let's say your u bar, the mean velocity, you will usually see this symbol called plus, u bar plus. You would have seen in literature, if you look at books, articles, you will see u bar. This plus essentially indicates that it's an inner scaling, that is, it is not divided by your u infinity or other u reference velocity, but the wall friction velocity. So this is nothing but your u bar divided by your u star, u bar by u star, and this particular is called inner scaling, scaling the your quantities using u star or u tau, wall friction velocity. Okay, similarly I can also do let's say the inner dimensional coordinate also. So I can also have this, since this is done, you would have also seen in some of the graphs what is called y plus. Now y is the coordinate like xyz, and you can represent this in a viscous inner coordinates. So this y plus is nothing but your y distance divided by your eta w, non-dimensionalized y. And what will this be? When I set this in, this will become u star y by nu. So y plus is u star y by nu. Y is known, that is known from your problem. Kinematic viscosity is known. As long as you compute wall friction velocity, you can have a y plus coordinates, which is your inner coordinate. Okay, so this is your inner coordinate. Okay, dimensionless, of course, inner dimensionless coordinate system, y u star by nu. Of course, you can also have an outer coordinate system that you can use delta, that you already know. Your y by delta will be your outer coordinates, that you already are familiar with it, how to use the boundary layer thickness. Now this y plus, is there a special meaning here coming in? If you look at it, u star y by nu, what does it look like? This is non-dimensional, right? So this is non-dimensional here. Does it look like a non-dimensional number? Yes. So it is representing a viscous Reynolds number. So we have a Reynolds number, a local Reynolds number based on the viscous length scale eta w and wall friction velocity. Okay, we are using a wall friction velocity and the viscous length scale. You are getting a local Reynolds number here. Okay, so y plus simply represents. So in a graph, you can plot, instead of y, how your RMS data is varying in terms of y coordinate, you can plot it in terms of y plus, and then you will know how your RMS or turbulence kinetic energy or your velocity changing with the local Reynolds number as y plus is increasing, right? So Reynolds number is not fixed. I mean, you can, some ask this question, what is this Reynolds number in a problem? In a turbulent flow, there is no fixed Reynolds number, because turbulent flows are characterized by eddies, right, vortices of different length scales. So you can define Reynolds number based on many different length scales, and we have already introduced here few of the length scales, like we have L, a very large longitudinal length scale, delta, an intermediate lateral length scale, and then the viscous length scale, eta w or nu by u star, which is the inner length scale or the viscous length scale, right. So 2-3 length scales have already been introduced, and you can define Reynolds number based on that. Okay, fine. So now we have this, and then yeah, so I told you that this graph, that there are many layers within a turbulent boundary layer. Okay, it is not just that there is an outer layer and an inner layer. This requires little bit of caution, or you need to look at it carefully one by one. I will guide you to see what this actually means. So now we have a wall here, okay, and then I already discussed about an outer layer and an inner layer, and I discussed about what is called a TNT, which is a turbulent non-turbulent interface. Okay, so this is nothing but a turbulent non-turbulent interface. So instantaneously it looks like this, and beyond that is what is called an outer flow. So whenever in literature you see the name outer flow, means this is outside the boundary layer, and inside the boundary layer, of course, that is inside your turbulent non-turbulent interface. This interface is extremely thin. It even has a name called Corsian superlayer. I will not go into the theory of that. That's turbulence theory, not the modeling part. Anyway, that the interface is very thin, and to know how thin, we have to introduce another scale that we will introduce little later. So there is an interface between turbulent non-turbulent zones, and below this interface you have fully turbulent boundary layer, and inside the turbulent boundary layer, which is of thickness delta as a function of x, I have two layers, which is outer layer and inner layer. And as you imagined, there is no sharp cutoff between these two layers, inner and outer. You are thinking there is a zone where outer layer is there and there is a zone where there is an inner layer. No, there is actually a gray zone or what is called an overlap zone. That's because in the outer layer, the equation, what was the equation we had? This particular equation here was u bar by dou x. This was balancing the turbulent term, right? So this term was dominant in the outer layer equation, right? And in the inner layer, the turbulent term is dominant, but it is balanced by the viscous term, right? So I have the viscous term, which is nu dou square u bar by dou y square v prime. That's in the inner layer. But there is a zone where both the viscous and or the turbulent effects are also there. The viscous effects are of course diminishes as you go away from the wall. So there is a zone above which viscous effects are minimal. Okay, only inertial effects prevail. So there is a zone, and this particular coordinate I am writing this whole part as y plus. So you can take this coordinate system here. Let's say I write this as, okay, can take this, okay. This is your x direction, and this I am plotting in terms of y plus. I will not use x plus because that is not a wall normal coordinate. Viscous length scale is defined for the wall normal component. So I have this y plus. So in y plus, if I go, there is a zone at which the viscous effects become negligible, and beyond that this outer layer becomes dominant. So I can now give values for this. So there is this particular zone where this inner layer will cease to be dominant is when I call this y bar. Y bar is nothing but y by delta is equal to 0.1. Okay, about 10% of your boundary layer thickness. So you can see it is already, boundary layer itself is very thin. In a turbulent boundary layer, it is even more thin, right? Extremely thin, sharp gradients you will see in a turbulent boundary layer. So boundary layer is thin, and this is 10% of that turbulent boundary layer is your inner layer. So very difficult to measure data in this for experimentalists. Extremely close, I know 1500 micrometers or so, depends on Reynolds number of course. So you are going very, very close to the wall. So this is the cutoff for this one, and of course the outer layer also ceases to be dominant when it approaches this particular zone, where that value we define as y plus equal to 30. Now I am using the inner coordinate y plus, not y bar, because I am inside the inner layer. So y plus 30 is when the outer layer is not so dominant. So in between y plus equal to, this is y plus equal to 0 and y plus equal to 30, you have two layers. One is called a buffer layer, the other one is called a linear sublayer. In the linear sublayer, okay, you will have what is called u plus equal to y plus. This is amazing here, okay. U plus is y plus, that is the name linear. So your velocity there is nothing but your wall normal coordinate y plus. Y plus is your coordinate, wall normal direction. So the behavior of the velocity is linear there in the linear, and the cutoff for that is about y plus equal to say 3, sometimes 5 in the literature, 3 to 5. So within this zone y plus equal to 3, you have a linear sublayer, y plus is equal to, sorry, u plus is equal to y plus, okay. So now we have already seen the data from how it looks like from wall to away of both the turbulent shear stress and the viscous shear stress, and then you saw that there is actually a zone where there is a cutoff. So if I go back to that graph here, so if I go back, now the values are, you already know what is this particular thing is now, let's say it is in y or y plus, it's actually y plus, it's not plotted like this. So now you know that it is y plus 30, okay, this is 30 here. So above 30 we said it is the turbulent shear stress is dominant here. So there is a zone, we said within y plus 30 there are two layers. One is a linear sublayer which is y plus 3, this is probably the first position or within less than that. Turbulence is negligible, only viscous shear stress is dominant. So u plus is y plus here, but there is a zone that is called buffer layer where both turbulent shear stress and the viscous shear stress are equally dominant. This zone is called buffer layer. Okay, this is a very important layer for turbulence physicists as well as turbulence modeling community, because this is the zone where maximum turbulence generation occurs. So the peak of your turbulence generation rates occur in this zone. You would have not recognized this when I showed the graphs. I showed the budgets of the RMS quantities. You would have not recognized where is that peak located. The peak was not on the wall for the production rate, right? The production rate was going up and then coming down like a hill, and the peak was located actually in the buffer layer. And the dissipation rates were maximum on, you would have seen that it is negative all the way but going maximum on the wall because it's a viscous dissipation rate. So now you understand from y plus coordinate point of view that this is the buffer layer where these two terms are dominant, and linear sublayer only viscous term is dominant, and far away only the turbulent quantity is dominant. Okay. So now we quickly take note of these three layers, that is linear sublayer, buffer layer and an inertial sublayer. This inertial sublayer also has, or this overlap zone has a name which is, some people call it power law zone or a log law zone. So there is a logarithmic law. What is this logarithmic law or a power law is, we want to relate this u bar, okay, in a logarithmic of y plus or a power law of y plus. That is what they want to do, right? So in a inertial sublayer, or this overlap zone is called inertial sublayer because inertial terms are dominant here compared to the viscous terms. So this logarithmic or overlap zone, this particular zone where you have this tau w here, tau w by rho, this is nothing but your u star square is minus u prime v prime over bar, that we have seen. Away from it, this is the dominant term here, okay. And in the buffer layer we had this tau w by rho equal to u star square is a combination of both. It is this plus your nu du dy. Both terms are equally dominant in the buffer layer, and here of course the tau w by rho equal to u star square is nothing but your, only the viscous term is dominant in the linear sublayer, okay.